In this lesson 8.1, we discuss about the nature of electric charges. If you are new to this channel, please do not forget to subscribe, hit the bell, and do some comments. I post educational videos at least twice a week. So let's get started. In this lesson 8.1, we have two goals. Number one, to describe the nature of electric charges and the rules of electrically charged objects. Goal number two, to explain the Coulomb's law and solve problems applying the Coulomb's law. The nature of electric charges. To understand electricity, we need to know more about the structure of matter. All matter is made up of atoms that are combined together into molecules. The atom is composed of protons, electrons, and neutrons. Protons have a positive charge. Electrons have a negative charge. Neutrons are neutral. Proton charge is equal to positive E. Electron charge is negative E, where E is 1.602 times 10 to the minus 19 coulombs. Atoms will have the same number of electrons in the orbit as there are protons in the center. For example, for a copper atom, there are 29 electrons and 29 protons. In many materials, the electrons are tightly bound to the atoms. Wood, glass, plastic, ceramic, air, cotton, and so on. These are all examples of materials in which electrons stick with their atoms. Because the electrons don't move, these materials cannot conduct electricity very well, if at all. These materials are called electrical insulators. Elements with more than 4 electrons in their outer rings make good insulators, as in the figures below. But most metals have electrons that can detach from their atoms and move around. These are called free electrons. Gold, silver, copper, aluminum, iron, and so on all have free electrons. The lost electrons make it easy for electricity to flow through these materials, so they are known as electrical conductors. They conduct electricity. The moving electrons transmit electrical energy from one point to another. Elements with less than 4 electrons in their outer rings make good conductors. Because of this, the electrons are easily dislodged from their orbit and pushed to the atom next to them, which is called the electron flow. We now know that all atoms are made of positive charges in the nucleus surrounded by a cloud of tiny electrons. Which type of charge is easiest to remove from an atom? A. Proton or B. Electron? The answer is electron. In fact, protons are vastly more difficult to remove, and for all practical purposes, it never happens except in radioactive materials. In this course, we will ignore this case. Only electrons can be removed. If we remove an electron, what is the net charge on the atom? A. Positive or B. Negative? The answer is positive. If we cannot remove a proton, how do we ever make something charged negatively? The answer is by adding an extra electron. Electrically charged objects obey two rules. Rule number one, Like charges repel each other. So positive and positive charges repel each other. Negative and negative charges also repel each other. Rule number 2. Opposite charges attract each other, such as positive and negative charges attract each other. Ways to electrically charge objects. Remember that when electrons are transferred from one object to another, both objects become electrically charged. There are two ways in which objects become electrically charged: by friction, by contact, and by induction. Let's consider now charging by friction. Number 1, when you comb your hair and bring your comb over a pile of paper bits, what do you think will happen? Some of the paper bits will be attracted to the comb. The force felt by the paper bits is due to a difference in charge on the comb compared to the paper. This force of attraction was first observed by the Greeks, who found that piece of amber or electron attracted other objects when rubbed. Another example of charging by friction is if an insulator is rubbed with a cloth, it can become charged in one of two ways. A. Electrons move from cloth to the insulator, or B. Electrons move from the insulator to the cloth. The third example is when you rub a balloon to your hair number of times. Can you explain what will happen? The fourth example is on triboelectricity. As the neutrally charged person walks across the wall carpet, his leather-soled shoes have less desire for electrons than the wall carpet. As a result, electrons get stolen from the shoe by the carpet. With every step, the person becomes more and more positively charged. That charge distributes itself over the body. When the positively charged person gets near the metal door, he will actually attract charges from the door which jump in the form of a spark. Notice how only the negative charges or electrons are free to move. It is important to point out that if he was wearing rubber-soled shoes on the wall carpet, his shoes would steal electrons from the carpet. He would become more negatively charged with each step. When he gets near the door, the electrons will jump from him to the door. From his point of view, it would look and feel the same as it did in the first example. He can tell whether charges jump to or from him. Human body cannot feel less than 2,000 volts of static discharge. Static charge built up by scuffing shoes on a carpet can exceed 20,000 volts. Look at the picture below and explain what is happening here. Now, let's consider charging by conduction or contact. The touching of any kind of matter, solid, liquid, or gas, can transfer a charge. There doesn't need to be rubbing or friction for a transfer to occur. In charging by contact, one object is already charged and the other may or may not be. For example, after you walk on a carpet, your body may be negatively charged. The doorknob is usually uncharged. Your body transfers the electric charge with the doorknob on contact. Actually, your hand does not even get to touch the doorknob before the charge begins to transfer in the form of a spark. Charging by induction. This involves the charging of one object by another without direct contact. A negatively charged object is brought near to a neutral conducting sphere. Electrons in the sphere are forced from the left side of the sphere to the right. The movement of electrons from the left side to the right side of the sphere leaves an unbalance of charge on the opposite sides of the sphere. A ground is brought in and touches the right side of the sphere. The unbalance of charge is neutralized as electrons leave the sphere and pass through the ground. The right side of the sphere has now been neutralized by the departure of electrons. There remains an unbalance of charge on the left side of the sphere. The positive charge remains near the negative tube. As the tube is pulled away, there is a movement of the remaining electrons within the conducting sphere, which results in uniform distribution of the positive charge throughout the sphere's surface. The entire process has resulted in the loss of negatively charged electrons from the sphere to the ground. Thus, the sphere has an unbalance of charge, having more protons than electrons. Discharging electrically charged objects. If an object has all the excess electric charges removed, it is said to be discharged or neutralized. All matter wants to reach neutral state, which means that it is neither positive nor negative. This means that if an object is charged negatively or positively, it wants to lose the charge to return to a neutral state. One method for discharging charged objects is by grounding. By connecting an object to a conductor wire, we are sending the extra charges into the ground. The charge is shared with the entire Earth. Storms and electricity. Lightning is a static discharge. Static discharge is a transfer of electric charges through the air between two objects because of a build-up of charges. Thunder is caused by the heat energy of lightning. How does lightning happen? Lightning happens when the negative charges or electrons in the bottom of the cloud are attracted to the positive charges or protons in the ground. The accumulation of electric charges has to be great enough to overcome the insulating properties of air. When this happens, a stream of negative charges pours down towards a high point where positive charges have clustered due to the pull of the thunder head. The connection is made and the protons rush up to meet the electrons. It is at that point that we see lightning and hear a thunder. A bolt of lightning hits the air along its path, causing it to expand rapidly. Thunder is the sound caused by rapidly expanding air. Static electricity. Objects can lose or gain electric charges. If something has an excess of electrons, it is negatively charged. A deficiency of electrons leads to a positive charge. The net charge is also sometimes called excess charge because a charged object has an excess of either positive or negative charges. A tiny imbalance in either positive or negative charge on an object is the cause of static electricity. Static electricity is the accumulation of excess electric charges on an object. Now let us consider Coulomb's law. Coulomb's law relates the force between the two single charges separated by a distance. According to the Coulomb's law, F equals K times Q sub 1 times Q sub 2 divided by R squared, where F is the force of attraction or repulsion in newtons, K is 9.00 times 10 to the 9 Newton meter squared per Coulomb squared. This is the Coulomb's law constant. Q1, Q2 are the electric charges in coulombs, and R is the distance between the charges in. The force between two charges gets stronger as the charges move closer together. The force also gets stronger if the amount of charge becomes larger. The force between two charges is directed along the line connecting their centers. Electric forces always occur in pairs according to Newton's third law, like all forces. Now let us do some examples. Example number 1. A 0.001 Coulomb charge and a 0.002 Coulomb charge are 2 meters apart. Calculate the force between them. Solution. We are given the following values. Q sub 1 is 0.001 Coulomb. Q sub 2 is 0.002 Coulomb. R equals 2 meters. And K is 9 times 10 to the 9 Newton meter squared per Coulomb squared. We are required to find the force between them. So using the formula F equals K times Q1 times Q sub 2 divided by R squared, simplifying, substituting the values and simplifying, we get the force between them is 4,500 newtons. Example number 2. Two equal charges separated by a distance of 1 meter experience a repulsive force of 1,000 newtons. What is the strength in coulombs of each charge? Solution. Here we are given the distance between them is 1 meter. K is 9 times 10 to the 9 Newton meter squared per Coulomb squared. The force is 1,000 newtons. We are required to find Q sub 1, which is equal to Q sub 2, and we will represent it by Q in the formula. So, from the formula, F equals K times Q1 times Q2 over R squared, or which is K equals Q squared over R squared. Rearranging to solve for Q, Q is equal to this R times the square root of F over K. Substituting the values and simplifying, the result is Q equals 0.003 Coulomb, which is equal to Q1 and which is also equal to Q sub 2. Example number 3. The first pair of 0.001 Coulomb charges is 200 newtons. What is the distance between them? So we are given Q1 equals Q2 equals 0.001 Coulomb. The force is 200 newtons. K is 9 times 10 to the 9 Newton meter squared per Coulomb squared. And we are required to find the distance between them. So from this formula, F equals K Q1 times Q2 all over R squared, rearranging to solve for R. R is the square root of K times Q1 times Q2 all over F. Substituting and simplifying, we get R equals 6.708 meters. Example number 4. The force between two charges is 1000 newtons. One has a charge of 2 times 10 to the minus 5 Coulomb, and the other has a charge of 5 times 10 to the minus 6 Coulomb. What is the distance between them? Here we are given Q1, 2 times 10 to the minus 5. Q2 is 5 times 10 to the minus 6. The force between them is 1000 newtons. K is 9 times 10 to the 9 Newton per meter squared, Newton meter squared per Coulomb squared. We are required to find R. So from the formula, F equals K times Q1 times Q2 all over R squared. Solving for R, we have R is square root of K times Q1 times Q2 all over F. And substituting the values and simplifying, R is 9 times 10 to the minus 4 meters. Example number 5. The force between two charges is 2 newtons. The distance between the charges is 2 times 10 to the minus 4 meter. If one of the charges is 3 times 10 to the minus 6 Coulomb, what is the strength of the other charge? So in this case, we are required to find Q sub 2. So from the formula, F equals K times Q1 times Q sub 2 over R squared. Rearranging to solve for Q2, we get Q2 equals F times R squared over K over Q1. Substituting the values and simplifying, we get Q sub 2 equals 2.962 times 10 to the minus 12 Coulomb. Thanks for watching. Please don't forget to subscribe.